Hello and welcome to the AI for Good webinar series. My name is Ida De Beer from the ITU, the International Telecommunication Union, and I have the privilege of introducing today's webinar. ITU is a UN specialized agency for ICTs, and we are also the organizers of AI for Good in partnership with 38 UN sister agencies and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI and scale the solutions for global impact. We are pleased today to discuss safety and robustness for deep learning with provable guarantees. We encourage you to ask questions in the Q&A box and use the chat to say hello. You can find these at the bottom of your screen. So without further ado, I would like to welcome our moderator today, Wojciech Samik, head of the AI department at the Fraunhofer Heinrich Hertz Institute. Over to you, Wojciech.
Yeah, thank you, Ida. I'm very happy to be back on track. So we had a long summer vacation period, but we are now back with the workshop series. So today we will have a great speaker, Marta Kwiatkowska. Marta is a professor of computing systems and fellow of Trinity College at the University of Oxford. She is further fellow at the Royal Society, at the ACM, and member of Academia Europaea, and has received various prestigious grants and awards, including the ERC Advanced Grants. And she is an expert in verification and correct by construction systems. And with this knowledge, she is currently very interested in the field of safety and robustness of AI decision-making. So I'm very happy to have you, Marta, and I'm glad to hear what you think about our AI systems and about provable robustness. So the stage is yours.
Okay, many thanks for the invitation and this opportunity to talk about my research. Let me just get started. Okay, so thanks again for the invitation and the opportunity. What I want to talk about is my recent work, sort of recent, in the past 4 or 5 years. I started looking at AI and in particular machine learning, and I started focusing on robustness. As you are probably aware, AI and machine learning seems to be taking over the world. Much of it is based on neural networks. Neural networks are loosely modeled on the way that human brain works, and they were first conceived in the 1940s. For a long time, about 50 years, there was no progress in that domain, but then starting from around 2000, they have been making great strides with convolutional nets and leading to the vision breakthrough and the win and go, and in fact the Turing Award, which is the Nobel Prize of computer science. So you might be saying, why now? Why not then? Well, this is because the technology has caught up. So in particular, what you have is you have multi-cores and GPUs in your computers, and there are also very efficient inference techniques to implement them. On top of that, there is big data. So we all have Facebook and Instagram, and there is a lot of data that has actually been labeled by humans and can be used for supervised learning. So because of that, because of that, there is we now have deep learning with, apology. There is some delay. I'll go back. There is just some delay. Sorry. Let's try again. I think it just seems to be jumping over slides. Can I ask for some technical assistance?
I think now we see. I think the slides.
Okay.
Now it's gone.
Okay, so because of that, we have deep learning with everything. What you see is deep learning is being used for face recognition. It is used in autonomous driving, and it is also being used for medical diagnosis. And on top of that, the stakes are being raised even higher and higher. So what Elon Musk is now doing is he's investigating brain-computer interfaces that, okay, some people say will make people telepathic. But because of this, because we are now putting AI and computer programs in situations that are potentially dangerous and potentially safety critical, the question that I have been asking is, should we actually worry about safety? So imagine yourself sitting in an autonomous car, and that autonomous car is going to have a controller, which is running a GPU, and there's actually a GPU grade a computer that is produced now for automotive applications. On top of that, it would also have a neural network, a deep learning module that will recognize traffic signs and traffic lights. And what I'm showing you here is real images taken by the dashboard camera of a car, and there was a challenge called the Nexa challenge. The challenge was to design a neural network that would classify these images into those which have a red traffic light or a green traffic light. And what we did is we took the winning network from that challenge, and the software that my student has developed could find in many situations just one pixel. If you take an image like this, which is classified as a red light, so you imagine your car is sitting at that traffic light, you find just one position, you change one pixel to green, and then the classification changes. So if that car is not using any additional protection, of course, the car will just start driving. So the question I've been asking is, how can we ensure that such behavior cannot occur? Of course, the example that I showed you before is, you might say, artificial, because what I've taken is I've looked at an image that the car sees. It's in its internal network. And what you need is you need an adversary that can actually break into the car to modify the pixel. But there are also attacks, physical attacks. And this is a real physical attack that has been discovered through resilience testing of Tesla. If you see the speed limit, you can see that the digit 3 has been slightly manipulated. Now that manipulation, this elongation in the middle, means that it was actually misread as an 85 miles per hour sign, which caused the car to suddenly accelerate. This was in a car park, so it was in a dangerous situation, but we know that cars like this are actually driving on highways. And of course, we know that there have been fatal accidents. So there was a Tesla, there was an Uber, and these were widely discussed in the media. But if you are one of those people who is actually devising neural networks for autonomous driving, you might be asking yourself, but how is it possible? I was told that these neural networks can learn and then they can have a 99.9% accuracy. And I will say something about this a little later to shed light on this issue. But first of all, my research area is focused on software verification. So if you take a piece of software, there is a little bit of code there on the left. What my research is concerned with is developing abstractions and models, rigorous mathematical abstractions of such software systems, and then developing also tools, mathematical and software tools that can actually prove that that software does what it's supposed to do. That is, that it satisfies the specification. Now, so far, until about 4 or 5 years ago, I have been working with models that are essentially automata annotated with additional information like time. But more recently, I've started also focusing on developing verification tools for neural networks. Now, another aspect that I'm looking at is synthesis. This is to what extent we can actually take a specification and automatically construct a system from such a specification in a way that it is guaranteed to be correct. And in my work, I focus on algorithmic techniques. That is something that you can implement in a software tool and release it and make it available. So this talk is going to be about showing you some examples. I will not have time to go much in depth and in detail, but the examples are concerned with how we can take software verification has been developed for conventional software and to what extent we can actually apply it to the case of neural networks. And if you are interested, you can look up some of these publications. So, okay, to start with, what we are going to focus on is deep learning, and that is neural networks. Neural networks are arranged in layers. In here, I'm showing you an example of, say, convolutional layers, max pooling, etc. And what they do is they take on the left an image. This is a point that lives in a vector space. It's a 3D matrix of a car representing the car. And what this point is then mapped through those layers until it gets to the final layer where it produces a score, and the score will indicate the most likely label that fits that input point. And in here, it's just showing you that the car, is the most likely label. Now, how does the neural network work? So this is the kind of the basic problem setting. So because I have several layers and I start with a point in a vector space, I need a series of vector spaces, one in between each layer. Now, an interesting question is, what is a specification in this situation? A specification is a classifier function. I'm focusing on image classifiers, and that specification needs to model a human perception ability. So if you show me an image of a car, I can tell you what it is. So this is just simply a function. Now, what machine learning does is it can learn to approximate such a function from examples. And these examples are going to be pairs of images and labels. So a car labeling a car, etc. Now, the neural network itself consists of layers. Each layer is a linear map followed by an activation function. the simplest activation function is the so-called ReLU, which is simply max of x and 0. Now, what we do is after we've decided what architecture to use, what number of neurons to use, you can then train this network so that it using optimization to actually fit the values of the weights and the bias that the actual deployed neural network uses. So that's the problem setting. Notice that, we're only talking about feed-forward and functions. There are no loops in here, but the complexity is really in the size and in the use of optimization. So once we've trained a network, what actually, in order to train the network, what we do is we select a set of training pairs, an image and a label. And I'm showing you here an example of how training works. You have two classes, say cats and dogs, the crosses and the dots. Now, there is a real task decision boundary, which is in a dotted line, because in many cases this is not known or it is very difficult to compute. So the trained neural network will learn some decision boundary, but these decision boundaries will not align. This is well known in machine learning, that they do not align. So what we do in order to check that the training has worked is we have another set of data pairs, which are the test data points. And what I'm showing you here is that these test data points are these darker blue crosses. Okay, now what this picture is also showing, so when you test, what you do is, okay, you've trained the network, you supply it with the test data points, and you just give it the point, check the output, and then the accuracy is simply the percentage of the answers that the network got correct. So 99.9%, that's what it means. But notice we are only working with finite data sets, but this is a potentially infinite, uncountable set within the model decision boundary. What these arrows from the darker blue crosses are showing you is how you can actually force the trained neural network to be unstable. If you use an optimization tool, you can then shift the input points to parts of the input space where there are weaknesses. And these weaknesses will be either on the border where the model decision boundary is misaligned, or between 2 points, because there may have been some points that you have missed out. So this is what model testing is. And that's why even if you have an accuracy of 99.99%, there will still be some errors that can be potentially fatal. So what I'm working with is I'm working with a concept which is known as local robustness, local or pointwise robustness, and I'm developing this really as a routine so you can use it within a safety assurance process. A safety assurance process is very complex, that involves sort of various frameworks. Here I'm working just on this routine that would take a trained network, work with some specification like this, and will tell you whether this specification, which is a very simple specification, holds for the network or not. So I'm assuming a trained network, and I'm also assuming I'm fixing a point. Here it's X is the point. And what I'm also assuming is that someone tells me that there is a region of points around the point X on which the decision has to be stable. And I'm going to then require that stable decision means the decision is the same as on that point X. So invariance in that region eta means that there does not exist a point Y which is classified differently. And this is what pointwise robustness is, and I'm working with this as a safety criteria. So in this case, you can simply imagine searching in that region and checking for misclassifications, which is what one of the existing algorithms can do. But what you can also do is you can try various more complex manipulations, and you can check invariance, for example, with respect to shifts, weather conditions, etc. Notice that one thing that I'm not telling you about is what distance metric to use. And that is because in computer vision, we tend to work with proxies, proxy norms, for example, L2, L infinity, even though what we really need is some similarity metric. So to show you what I'm trying to do is on the same diagram, what I'm trying to achieve is model verification. So I'm trying to have these complete green regions covered with which I know that decision is going to be robust there. So even if you try to start with a dark blue cross the test point and try to look for weaknesses, you will not be able to find that within the green region. So that's the difference between verification and testing. So safety verification, well, the very first approach that we used and for this simple property is that it simply tries to rule out adversarial examples. An adversarial example is a point which is a very slight perturbation of the point X, very slight perturbation, so it should be classified the same, but it isn't. Now you can check, there are no adversarial examples. Under some mild conditions, you can discretize the region so that you have a finite search space, and you can search for misclassifications. And if you have not found it, from that you can deduce that there are no adversarial examples. Notice that this is rather different from heuristic search using optimization, because if you haven't found it using heuristic search in a continuous space, you cannot conclude that adversarial examples are not there, not even in a small region. But of course, this very first method that we tried turned out not to scale very well. So then we tried to do something else. But of course, the problem that we are dealing with is very high dimensional, and neural networks are also known to be nonlinear. So if you consider an image, this image here, this image actually has 24 million dimensions. And trying to search for the one pixel, that you can change so that the traffic light classification changes, that very quickly becomes infeasible. So what my student did in this case is he applied structure to the problem. And in fact, this employed a method, the well-known algorithm in computer vision, which is known as the sift algorithm. What the sift algorithm can do is, it can take an image like the one on the left and then produce a list of salient features together with their position and how important they are. So these circles that you see there, they just show you the relative importance of the features in the image. Now you can then use this list of features and produce a representation as a Gaussian mixture model. So what I have is, I have an image like that, I process it using sift, but then I have an intermediate representation which knows about the features in this image and how important they are. Why is it useful? Well, because I can then, depending on the importance of the features, I can weight my search. So I can guide my search depending on the importance of the features. In this way, I am more likely to find the most harmful adversarial examples sooner. And in fact, what we do in this case is we set up a game. Now, games have been used in machine learning for reinforcement learning. And for example, they have been used also in the Go playing game, and we are using here a very similar method. But in this case, what we are trying to do is we are trying to take a trained neural network on a particular image and try to explore its stability. So by searching within a region around that image, and to search effectively, what I do is I set up two players, and player one, rather than select one of the 24 million pixels, player one selects a feature, and that's the feature that will be manipulated. And then player two will select a pixel within that feature. So if you choose the most important feature, then quite likely you will find problems with that feature very soon. Now, these players alternate, and I set up as a reward an inverse of the distance between the image and the manipulated image. And in fact, what can be shown that with this, I can compute an approximation, in fact, two approximations of the so-called maximum safe radius. So for an image, there will be a maximum safe radius such that within that radius, all images will be classified the same. It is impractical to compute, but I can compute an under approximation, a lower bound, and an over approximation, an upper bound on the MSR. There are different methods. For the upper bound, I use Monte Carlo tree search. For the lower bound, I use a variant of A-star search. But this is an example of how the tree expands. Since images are just finite matrices of pixels, I start here by finding a feature and then pixels within the feature. This is a finite game. Perhaps it would have a lot of branches, but it's a finite game. But if you follow this route here, you will see, to start with, some of the modifications do not cause instabilities until the one in the red border here is the first one, which is an adversarial example. It still looks the same as 7, but the network classifies it differently. So what can we compute? This is an example which uses an image from a set of German traffic sign images. And I'm showing you how the upper bound, that is finding adversarial examples, converges to a lower bound on this, and the images at the top are not adversarial, they are safe. The network's decision is the same. Now, this example is for images. What you can do is you can also extend this method to videos. Here, the models are much more complex because we use a combination of a convolutional network, which extracts features, and the recurrent network architecture, which processes the frames of the video, and the perturbations are actually not of pixels, but of optical flows. Optical flows are the differences between the positions of pixels in the consecutive frames. But you can see a similar kind of picture of the upper and lower bounds converging. So the idea is that these lower bounds are guarantees. If you can guarantee that the perturbation, because of the noise or something, is not greater than the lower bound, then you guarantee that the network's decision is safe in that region. Anything that's greater than an upper bound, that means that there is definitely an adversarial example, so it is not stable to use. There are also extensions of this method to text classification, which I will not explain, but you can look this up if you are interested. And I will finish by saying what this method has allowed us to show for the Nexa traffic light challenge. So remember, I showed you these were real dashboard camera images. Now, what we were able to show using this game-based method and Monte Carlo tree search is if you take a set of test data points, data pairs, for each of those, this method was able to find on average 3 pixel changes. So in many cases, just a single pixel, on average 3 pixel changes in less than a second per image, such that this image was misclassified. So that means if instead of using that the original test data set, you supplied the slightly modified one, which to a human would look the same or almost the same, the network's accuracy, which was 95%, went down to 0%. Notice that I've shifted the distribution slightly because I went beyond the test data set. I allow here modifications to the data set, but this is quite common in adversarial situations. But of course, this leads me to also question, but how good are these maximum safe radius guarantees? This is still a very, very simple property, just to look, say, at an image or a video and a region of, videos that are very similar to it. Say, they differ by some very minor, potentially imperceptible perturbation. There are positive things about this method that I've just introduced. It is model agnostic, can be configured with different norms, and metrics can be applied to discrete and continuous searches, but the focus on local robustness is still very, very limiting. And in fact, what we need to consider is not just robustness to noise or perhaps minor adversarial perturbations, but robustness to interventions. So there could be an intervention. What we call an intervention is an environmental change to the input. say you train your network in California and then you take it to London. So while you were training your, say, autonomous driving car network in California, you are more likely to have, sun, etc. And then you take it, and in London in November, the skies are gray and the network just stops working. So this was a shift and an intervention that you have performed on the input data, and you need to consider such shifts. And another aspect that one also needs to consider is, well, so far, I only told you about deterministic guarantees. So the guarantee that the MSR provides is, well, if I have an image and given some metric, as long as the perturbations are bounded by the lower bound, I can guarantee that the network will behave stably in that small region. But in fact, training is a probabilistic process. It involves conditioning on the input data. And what we need to consider is not just deterministic guarantees, but probabilistic guarantees that can take account of the learning process. So I'll just show you, for example, what we are doing with robustness to interventions. We are working in this case with causal Bayesian networks. They represent families of probability distributions, and we are working on techniques to actually upper and lower bound guarantees with respect to certain shifts of these distributions. I'm looking at the time. Okay, so I think I will skip it, but if you are interested, there is a paper this year where we consider interventions, both parametric interventions, but also interventions that change the causal structure, change the causal links between the dependencies in the Bayesian network. And I will finish with probabilistic guarantees, again, just to give you the intuition. So because the learning process is actually probabilistic, deterministic guarantees are not good enough in many situations. And in safety critical situations, we have to work with probabilities because you cannot actually rule out an accident. The best that you can do is you can minimize the probability of the accident to something tolerable. So instead of working with neural networks, we can work with so-called Bayesian neural networks, and these add probabilities, but by putting a prior on the network weights. And for this, what we can show is we have applied it to neural network car controllers, but they are now Bayesian neural network car controllers. So the guarantees that we obtain are probabilistic. So what you see here is I can actually estimate the probability of the car controller being safe in different situations. So these different situations can correspond to the weather. The picture there at the bottom is actually a picture from the simulator, not from the real car, that's from the Carlo simulator, but it shows bad weather, so rain or snow, and the picture above is, perfect weather, and these images would then be fed into the network, and the network will be considered as input into my software tool, which would perform this safety analysis. And we have also used it for various kinds of inference. Now, just to summarize, where I am, I've started off by saying that there is a lot of excitement about AI and machine learning, and in particular neural networks, and much of that excitement is very well placed. Sorry. But unfortunately, what we also need to consider is that there are risks in deploying these solutions in safety critical contexts without actually performing proper safety assurance. And there have already been examples of significant investment into new systems that had to be withdrawn because they didn't work as well as they could have done. And I will just finish off by summarizing that deep learning, of course, it has tremendous potential, but it needs to be critically evaluated when it is put in practice in safety and security critical situations. What I've shown you here is just one stream of techniques that I've been developing in my group that aim to focus on safety verification, also testing and computing worst case guarantees on the behavior of the network, but also moving towards probabilistic guarantees. But there is much more work that is needed. And in particular, I would highlight here strategic and distributional robustness. We also need robustness against strategic behavior of agents, and an aspect that is still very, very much under-researched in this context is correct by construction synthesis. So to what extent we can actually train a neural network and then perhaps repair it, so we train it, we check it, and then perhaps repair it to actually guarantee that that neural network will behave correctly for all inputs. So thank you.
Yeah, thank you. Thank you very much, Marta. Do we have questions from the audience? So maybe I will start with one. I mean, when we go back to adversarial robustness, do you think? I mean, do you think it's also like a problem of the architectures, the models we are currently using? Because humans, for example, they not only have a bottom-up processing, but also like a top-down processing, and they use also knowledge, world knowledge, to show robust behavior. For example, if I see a stop sign with a sticker on it, I still know that this is a stop sign because I know the concept of a sticker, and even I see this, my kind of my top level knowledge tells me that this cannot be another sign. Mm-hmm. Whereas like neural networks just get the pixels and don't have any other context and any other knowledge they can derive these kind of conclusions from. Do you think we need this kind of novel types of models to be really robust?
Yes, so there is, but I would say there is a great debate about this. So I think some people describe it as what AI just doesn't reason based on common sense. But we humans use knowledge, and the way that neural networks learn, even though this is described as learning, the way that children learn, in fact, this is very, very different, because we learn, we accumulate knowledge, and we learn knowledge. There is a debate now in the community about to what extent what we actually need to develop is combinations of neural systems and symbolic systems, and this is known as neurosymbolic. So where neural networks perform really, really well is in pattern recognition. And pattern recognition is sort of low level perception function. And in these situations, neural networks should easily beat the human because they are faster and they have more power. But in order to develop systems that behave like humans, what we need to combine is knowledge, so reasoning with graphs, knowledge networks, and perception. So that is a great challenge. Although some people believe that neural networks can do everything, I personally don't.
So we have a question from the audience. To which extent are adversarial samples generic enough to represent real-world perturbations, domain shifts?
Well, so this is something that I'm not working on myself, but there is a whole aspect and a set of tools called generative adversarial networks, and they've made tremendous progress there. So you can actually learn very realistic adversarial examples using those techniques. I think the examples that I showed you were, quite artificial.
Mm-hmm. Mm-hmm. And maybe to follow up this question, is it more difficult to give guarantees for targeted attacks, like adversarial attacks, compared to real-world domain shifts when you train a network in California and test it in London, or is the guarantees for the other case more difficult to get?
Well, I think even simple distribution shifts, we can't provide guarantees. So when I say, guarantees, if you mean provide guarantees for all possible inputs, I think this is what we would like to have, but we can't at the moment. That is just not feasible. Perhaps with high probability, we can provide some guarantees, I think, on certain distribution shifts, but on all the possible distribution shifts.
I see.
So you can consider, for example, change of, what I can do now is change of lighting. But I do change of lighting. I cannot do, for example, the change of camera angle. This would be a separate problem.
Yes. I think if you know this possible changes beforehand, then you can integrate it also in the training in some kind. Maybe another question. So I'm interested in explanations and interpretability of neural networks. And there has been recently some work on also adversarial attacks on explanations. Are you familiar with it? And are you working on this kind of topics?
Yes.
What is your opinion on that?
Yes. So that's right. So explanations can also be manipulated. I mean, I would say any software can be manipulated. I think if you have, some channel on which you can attack, then I'm sure it can be manipulated. So yes, we have some work in this domain for NLP, natural language processing, where we can produce explanations. We call them optimal robust explanations. So they are actually robust in the sense that, they will not change if you perturb them. And they are explanations in a sense that they imply each of these, but you may get a very large set. Each of these will imply the network's decision. So for this, we've used satisfiability modular theory tools to compute them. But they are robust. So yes, I think people are ultimately very clever, and I think any defense so far, people have produced a lot of defenses for adversarial examples. Every single one has been broken.
Yes. So we had some interesting speaker. I think he's one of the guys who are really breaking all the defenses. At some point. Yeah. Do we have any other questions from the audience? So maybe I would like to have some final question from my side. How does your approach? So I mean, you use the sift features as important masks for sampling. How does it relate to gradient-based attacks? Because you could also use the gradient to compute this importance mask, or you could use an explanation to do it. I mean, how have you compared it, or how does this relate to this kind of attacks?
Well, we haven't compared it. So there, the advantage of sift is that it is a fast performing method. Now and it's because the actual problem was then focused on computer vision. It behaves similarly, but of course we don't know if it behaves identically to the way that the neural network identifies the features, but it behaves similarly.
But do you assume that you have access to the neural network, or is it like a black box attack where you don't have access?
It's black box, that's right. So I can use it as a black box. I just pre-process the image, but then once I have a mixture of Gaussians representation, because it's a mixture of Gaussians, you can reweight the probabilities. I can try to align that intermediate representation with the features that the network sees. By reweighting the probabilities.
And could you include this kind of procedure into the training process, as people did with the adversarial training?
Yes. So we haven't done it. I mean, the very first approaches, I think the very first adversarial attacks just argued that you should just include some more adversarial examples in the training, but then of course it's very easy to show that you can then bias the training. So yeah, it is not the answer. It is not the answer. I think for me the real answer is, combining this common sense reasoning based on knowledge with perception based on neural networks. So ideally some kind of neurosymbolic system.
I see. Yeah, I also have the same opinion. I also think that we need to go beyond what we have to get really trustworthy models, and especially when we want to apply it to sensitive applications. We cannot do it with the current technology. Okay, if there are no other questions from the audience, then I would like to thank you, Marta. It was a very inspiring talk. And yeah, I would head over to Ida to do for the concluding remarks.
Okay. So sorry about the timing issues. For some reason, either my Mac or there was some interaction between the systems, which skipped over some slides. Okay, thank you. Thank you for the invitation again and the questions.
Thank you very much, Marta and Wojciech, for a great session and interesting discussion afterwards. We are opening a quick poll now with just one question. Please answer and let us know how much you liked this session. And feel free to rewatch this session on our AI for Good YouTube channel anytime and share with your friends and colleagues. We also encourage you to check out the AI for Good program online to see more sessions that may be of interest to you, including future and past sessions in this Trustworthy AI series. We will post the links in the chat soon and encourage you to join. We would also like to thank everyone involved, Marta, Wojciech, our participants, partners, sponsors, and co-convener Switzerland, and we hope to see you again soon.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector.